Welcome to the technical talk for the CSE research community on exploratory analysis for unstructured data. I'm Leland McInnes, and I'll be giving you an overview of some of the more technical side of our research core. So let's first talk about unstructured data. Structured data is just the information that has a nice predefined schema. It's usually in rows and columns. It's a database or a spreadsheet or something like that. Think tabular data, nicely formatted, easy to parse. Unstructured data is quite literally just all the rest, everything else. So that means things like freeform text, it means images of all sorts of resolutions and types, video, audio, all sorts of things qualify. But it also extends to all kinds of other things that CSE would be interested in, things like source code, system logs, malware binaries, network flows. These are all pretty open freeform kinds of data that are unstructured and we still need to work with. Now, that means that the vast amount of data that we actually create and store is actually this unstructured data. We haven't stored everything in nice, tidy knowledge databases with careful schemas. We have data of all different kinds, and we somehow need to deal with that. Which brings us to the question of doing exploratory analysis. The first step in any data-intensive project is gaining an understanding of what's in the data before you start. For structured data, there are a lot of many well-established techniques for doing this. Data cleaning for tabular data is largely well understood. You can go to summary statistics, there are visualizations, faceted plots, and so on. Clustering and outlier detection are reasonably well defined for this kind of data, and data profiling, data types, missing data, these kinds of things bring out all the other things you might be looking for. So we can go through and get a pretty good understanding of the content of a structured data set pretty quickly. For unstructured data, things are a lot more challenging. Techniques tend to be data type specific. You have something specific for dealing with a particular kind of text or a particular sort of class of images. And these can tend to scale pretty poorly. As you get up to larger and larger data sets, this gets harder and harder. So we'd like to build a standard universal technique or set of techniques for exploring unstructured data in general. So let's talk about exploring unstructured data. Our pipeline for doing this is roughly as follows. If we have techniques for vectorizing the data, turning unstructured data into vectors where there's a meaningful metric between the vectors that captures some of that domain-specific knowledge about that kind of data that we want, then we can hand that off to approximate nearest neighbor search. That leads into clustering and dimension reduction. We can bring those together into interactive visualizations, and from there, we can get disposable local models. So some of this is one end is a vector database. Really, that's there, vectorizing the data and approximate nearest neighbor search. Vector databases are pretty common these days. The other end of this is really managing to generate new hypotheses about what's in the data, and then quickly and easily build and test those hypotheses. So what we want out of that is feedback from those hypothesis tests. We can alter how we vectorize the data to capture more information or change what we're doing, change how we view things. We can feed that back into the dimension reduction, the clustering, and so on to help generate new hypotheses about what's in this data. And again, we can build models to test those hypotheses and again, feed this back. This creates a very virtuous feedback loop where we get to improve the quality of our data and our understanding of the data a lot more quickly. So let's now talk about all those different stages of that vast pipeline that we're talking about for our approach to exploring unstructured data. The first is vectorizing the data. What do I mean by that? Well, it means taking some pile of data of some kind, documents, images, some combination thereof, doesn't matter, feeding it into some system that then spits out vector representations of that data. So the trick is to turn unstructured data into vectors where the distance between them is meaningful. In other words, I want, if I'm dealing with text, documents that are similar in some way to end up with a small distance between them. Now, the catch is, what does similar mean? It might mean that content of the document is very similar, but there's also authorship attribution style embeddings where what we want to do is have documents that have a similar authorship style, were probably authored by similar authors, end up close together. So exactly what you mean by similar matters in this vectorization step, but that's where we're going. Now, neural embeddings work really well here. There are a lot of those around. You can take images, audio, video, text, hand it to your favorite neural embedding model. That could be OpenAI, Cohere, Anthropic. Hugging Face has innumerable options that you can just download and use, and they spit out vectors for you that capture a lot of meaningful things about these standard data types. But there's no one true embedding. Depends on what meaningful means for your data. So we're going to have to explore a lot of different ways, even if we have a good text embedding. That might be with respect to one thing. We want the ability to have different notions for text about what it means to be close. So what are the current solutions in this space? As already mentioned, there's OpenAI, Cohere, Anthropic, Hugging Face. We at the Tutte Institute have developed a library called Vectorizers, where we are targeting rather more specific kinds of data in cyber defense contexts. We're still trying to be very general, and we're trying to use foundational rather than neural techniques, so much more focused on matrix factorization or other standard techniques like that, but hopefully building a robust, generalizable approach to some of this vectorization. What are the outstanding problems here? Isn't this already solved? We have these neural embeddings. Well, you can always get better quality embeddings and more meaningful distances, different kinds of meaningful distances. New data modalities are critically important. A lot of the unclassified work on this is all in images, video, text. But as mentioned, we're interested in source code, system logs, network flows, all kinds of other data for which there aren't already embeddings that work. Multimodal embeddings where we're jointly embedding images and text, so you can search for images with a text query. These are incredibly powerful. Being able to build that out to support a wide range of modalities other than just images and text, especially the modalities we're interested in, some of these cyber defense modalities, these would be incredibly valuable. And novel embedding approaches. We already mentioned the Vectorizers library is focusing not on neural embeddings, but on other techniques. We'd love to see more interesting techniques that can still work very well and particularly could apply to a much wider range of data than is currently being used. All right, let's talk about approximate nearest neighbor search. So given that we have some meaningful distance between objects, finding nearby neighbors becomes critical. Find me things similar to this is what we want to be able to ask. So that means scaling vector search to massive data sets. And it turns out that's actually quite hard. We can't scan the entire set of vectors anymore and measure distance to everything. We need to prune that down. So there are, in fact, good techniques. There are graph-based techniques that allow you to quickly search toward a goal that is close, find all the nearest neighbors without having to traverse the entire data set. There are other techniques as well based on vector quantization. We're open to anything that anyone is interested to work on this. The problem is also a fundamental one in that it feeds into both the clustering and dimension reduction steps that follow. Most of the good clustering and or dimension reduction techniques that we're going to discuss shortly all rely on quickly finding nearest neighbors of points. So what are the current solutions in this space? There are innumerable vector databases out there, Weaviate, LanceDB, Qdrant, Vespa. We have a library called Pioneer Descent. That was what the video was from, doing a graph-based approximate nearest neighbor search. Our goal with that was to specialize again to the kinds of data that we are interested in, including sparse data and a wide variety of distance metrics. What are the outstanding problems in the space? Scaling to truly massive data sets. Distributed approximate nearest neighbor search is still somewhat of an open problem. Another thing that Pioneer Descent focused on was KNN graph construction. So rather than building an index and searching for points one at a time, I want to build a graph of the K nearest neighbors for every point in a data set from the outset. So doing that very efficiently without necessarily having to build a giant index first would be very valuable. Constrained search, where we're possibly only searching some subset of the data in the vector database, that would be very valuable. And hybrid search, where we're searching with other methods as well, say TF-IDF or BM25 or other keyword-based searches. This feeds back into the constrained search. These are all open problems for doing it really well. All right, let's talk about clustering. So clustering is finding similar groups within a data set. So regions of the data where groups of data clustered together tightly and have relative similarity in and amongst themselves. When data sets are large, that means we can extract a summarizable chunk of it. And this is incredibly valuable for that exploration step. For embeddings, especially neural embeddings, this amounts to clustering high-dimensional vectors. So topic modeling by clustering sentence embeddings is a pretty successful prototype. There are a wide variety of tools out there at this point for doing topic modeling with this kind of approach that have become very popular. So what are the current solutions in this space? Well, BurTopic is probably the leading topic modeling approach using this. Combinations of UMAP and HDB-scan are also incredibly valuable and are indeed the default in BurTopic. We're also working on other libraries like Evoke, which targets high-dimensional clustering specifically. It's embedding vector-oriented clustering. We want to aim specifically at clustering embedding vectors as efficiently as possible. What are the outstanding problems in this field? Well, high-dimensional clustering is just hard in general. High-dimensional vectors tend to break a lot of our assumptions about what clusters look like and how to find them. So a lot of the classical algorithms just don't work very well on high-dimensional data. A lot of the current techniques involve a dimension reduction step. It would be great to not require that and move to a stage where we can do the clustering directly in the high dimension. Scaling performance to really large data is critical. We're going to face ever-growing data sets, so we need truly scalable algorithms. Multi-resolution clustering is another big problem. Finding different layers or hierarchies of clusters, whether you want a top-level view with very large clusters or you want to get down in the weeds and have very specific clusters that pull out detailed information, this is a non-trivial problem, and doing it well is still open. And finally, semi-supervised clustering. If we can get some information about how an end user would like to view these data points being clustered, can we feed that into the clustering algorithm to help it pull out the kind of information the user is looking for, the kinds of groups that the user is looking for, rather than merely whatever it can find with a purely unsupervised approach. Dimension reduction. What's dimension reduction? It's taking a giant set of high-dimensional vectors and turning it into a lower-dimensional set of vectors. In this case, the image on the right is when we reduce to a mere 2 dimensions and then put a point on a scatter plot for every single point in the original data set. Here's an example of that with the MNIST digits dataset, where we've reduced the 784 dimensional handwritten MNIST digits down to a mere 2 and represented each digit by an actual image of the handwritten digits. You can see that it groups the digits by their class, but also within the classes, you can see the changes and variation within how the digit is drawn, style changes, and so on. So it's capturing a lot of information from this very complex high-dimensional data set very efficiently in 2 dimensions that you can present to a user in a visualizable way. So if we're going to be able to present high-dimensional data for exploration, we really want a visual representation that a user can just grasp. Visualization is the high-dimensional, high-bandwidth channel for getting information into someone's brain. The classic quote from J.R.R. Tolkien is that there's just nothing like looking if you want to find something. Being able to present something visually where somebody can see it makes such a difference. And importantly, you often find things that you weren't looking for in the first place. And that's really the key to the hypothesis generation step that we're looking for. Whenever you present someone with one of these plots where it's data that they know and understand about, almost always their first question is, what's that? Why is that there in this plot? And that leads to new questions that they end up exploring and finding new things about the data that they didn't know before. So dimension reduction is a great tool for finding and providing these visualizable representations. What are the current solutions? The primary ones are UMAP, Uniform Manifold Approximation and Projection, developed by the Tutte Institute, and OpenTSNE, which is a very efficient implementation of the TSNE algorithm. What are the outstanding problems in this space? Well, improving the quality of these dimension reduction results would be something that there's still a lot of space to do. Another key point is interpretability and explainability of the results. Right now, techniques like UMAP and TSNE are not really as interpretable or explainable as we would like them to be. Scaling performance to really large data is still an open problem. Another interesting question is multi-resolution for large data. When you take a really large data set and apply these techniques, you can get clusters out. If you subset to just a small amount of the data that was in one of those clusters and run on just that, you get interesting substructure within that. Being able to do this in one step and present a single high-level view that you can zoom in on and find these substructures represented at different resolutions, that is something that we would really like to be able to see. And finally, smooth incremental updating of the data. As we have new data streaming in, we want to be able to add it to the visual representation in a way that makes sense. If there's a new cluster that's going to form somewhere, we want to actually represent that fact and have the visualization update, adding these new points and spawn off a new cluster as needed, and so on. This is a very difficult challenge for a lot of the current state-of-the-art techniques that are generally graph-based. All right, let's talk about the interactive visualization stage. There's a paraphrased quote from Hadley Wickham: models scale, but they never surprise you. Whereas visualizations can surprise you, but they don't scale. So we need to make visualizations scale through interactivity and exploration. So let's take some lessons from Google Maps. A smooth interactive pan and zoom makes all the difference. Multi-resolution labels, country, state, city, suburb, street names, these allow you to navigate through the data at different levels of granularity and understand the data in high-level views or in a great deal of detail. Being able to search and summarize is critical, and access to the raw data via that map. So I can, in a Google map, click on a point, and if it's a famous building, it will tell me all about that, and so on. Getting back to that core information that we actually want to understand, this is also valuable. We need to link that through whatever map we present. So that means we need cluster naming, we need to summarize selections, we need to be able to overlay metadata to see how that metadata looks with respect to the visual representation we've provided. So what are the current solutions in this space? Nomic Atlas is a great approach to this. It's a closed-sourced company. Graphistry is another great tool for doing some of these sorts of things. Again, very graph-focused, but has a lot of great interactive approaches to this. Again, closed-source for the most part, company-based. We've produced at least a couple of packages, Data Matplot and This Not That, for interactive exploration of large data maps. We'd love to see more solutions in this space. What are the outstanding problems? Features, features, features. Managing to get the different ways of exploring that data accessible to an end user. There's just so many different things that need to be added or available or optional, and none of the solutions out there have all of them in one package. Everybody has a slightly different set of features, and we'd just love to build a common platform that can build up a broad base of features available. Scaling to really large data remains an open problem. Labels, having cluster naming for things other than just text. With topic text, we can do topic modeling, we can get topic labels, but for images, what do we do? For video, what's the right approach? For software or malware binaries or system logs, how do we do that? These are still open problems. And It would be great to bring some HCI, human-computer interaction expertise to this problem. We at the Tutte Institute are largely mathematicians and computer scientists. HCI is not really our primary skill. We're doing our best, but we'd love to have a lot more expertise from people who really know how to do this well. The last step in all of this is disposable local models. What do I mean by that? Well, explorable maps help us ask questions and generate hypotheses. But how do you answer questions and test hypotheses? And the best way to do that is make model building accessible directly in the interactive visualization. I want to be able to select some data points and say, what's going on here? Build me a model to test the hypothesis that this is a relevant piece of data in one way or another, and have it apply that model across the data and give me some results quickly and easily. So that means the models need to be robust, explainable, and largely parameter-free. And then can we feed those results back into the earlier stages? Can we improve the vectorization based on a model that has driven by end user information tagged to the data in some way with respect to different classes that we need to separate or bring together? Same with dimension reduction and clustering. We want those to be able to solve the user's needs, not merely do it in a purely unsupervised way. So if the user can inject information via building these models that can classify subsets of the data in ways they care about, that's what we want to be able to do. What are the current solutions in this space? To be honest, this is a bit of an open problem. We want fast, easy to build models that are robust and efficient. So our best guess is some kind of robust KNN based classifier, but we're open to any suggestions for something that is simple, explainable, and robust that can be generated on the fly interactively, easily. What are the outstanding problems? Well, what's the right model class for the job? We've suggested robust KNN classifiers, but we really don't know the answer. Another key is actually integrating this into those interactive visualizations. We want to make this as accessible and easy to use as possible. And then how to apply those feedback mechanisms back into the rest of the workflow. All right, let's have a look at an example of some of this workflow put into action where we've done vectorization, dimension reduction, clustering, labeling, and have at this point an interactive visualization. So let's look at a live demo. Here is data from arXiv. This is 2.5 million papers published on arXiv, a data set of preprints. We've organized this data. We've vectorized it with nomic embed, a text embedding model. We've dimension reduced it with UMAP. We've clustered it with HDB scan. We've done that in a hierarchical way. So we've got layers of clusters, and then we've used large language models to generate meaningful labels for those clusters. So right now, you can see there's a cluster that's about machine learning theory and applications. There's algebraic structures and topology. And if you zoom in, you can see the lower level structure here. So algebraic geometry and cohomology, algebraic geometry and moduli theory, and so on. If you zoom out, we can zoom in on the machine learning section and understand different regions and subcategories within machine learning. We've built all of this so that there is search available. We search for learning. You can see we're going to highlight the machine learning area. Same if we search for neural, oddly enough. Very few other regions are interested in neural, less so physics. We can also hover over these in time. There are regions of this where that can reveal interesting information. Wireless communication networks, if you start in the early days, information clusters in one region, but as you move up, it moves and clusters down in the bottom corner there. What's going on there? That's about intelligent surface networks. It's about changes in the style and technology of wireless communication, and the problems become different. We end up in a different region of the space. We can even select and see specific information about the titles that are available there. All right, moving on. Let's sum this up. We have the opportunity to build powerful tools for exploratory analysis of unstructured data. We have some initial open source tools already. The Tutte Institute has put out a number of these: vectorizers, Pioneer Descent, HDBScan, Evoke, Uniform Manifold Approximation and Projection, this not that, data map plot. But this is just a starting point. Any or all of these can be improved, replaced, or built on top of. There's so much scope to make this better, more integrated, and more efficient. So what we want is an open source ecosystem for exploratory analysis of unstructured data, bringing together a suite of tools that can work together to perform all the different tasks we've described here. We want to use solid math and CS foundations to build these tools. We want them explainable and robust with good theory behind them. And we want to bring in HCI and user experience expertise and have interdisciplinary teams that can cover end to end from the math side to the computer science and software engineering side to the user experience side to make it as accessible and usable for as many people as possible. The call for proposals is open. QR code here will take you to that call. If you want to get in touch with us, you can reach out at these email addresses. Thank you.